This is an equipment update for the ETE335 laboratory. Primarily this is associated with a new oscilloscope which was put into the lab last year, and its associated function generator. So we'll go ahead and turn these units on. These are modern digital instruments, and there's a couple things you need to know about these instruments. One is they can store settings for the users. Now this is both a good and a bad thing. If you're a user that only uses this machine, you can preset values and for probes and a variety of things. But as a user, one of many users, you might want to take a few steps ahead of time to make sure that the instrument is in the condition you expect when you come in. Now most of these are under the button Utility. Under Utility we'll see System. Now you can see right here the system power on can be default or last. It's a little better to use the default button because then you know you're going to start with the system settings from the manufacturer. Another element in the utilities is in the calibration. Now calibration is important because this means you can check the instrument by itself. Now you can see in this case the instrument was last calibrated on April 4th, today, so that's not a problem. When you calibrate, you have nothing connected. If you press start and calibrate, it takes about 5 to 10 minutes to do the calibration. So if it was recently calibrated, no need to do that, but if you walk into the lab you could, and it hadn't been calibrated in a while, you can do that. Alright, now we're going to set up the lab to take some measurements. So the circuit we're using is very straightforward. We have a signal generator, which is going to be our arbitrary waveform generator. We have channel 1 and channel 2 on the scope, and we're going to use scope probes with that. So we see the input, the red, channel 1, channel 2, and then the grounds. First, let's set up the generator. Alright, so here's our arbitrary waveform generator. The defaults are 1 kilohertz sine wave with 5 volts peak to peak. It's always good to start with a high level signal that makes your low level measurements easier to make. So we happen to be using 1 megahertz in this case. That'll be a test frequency, so we'll go ahead and set the frequency. Variety of ways of setting the frequency. You can either adjust the knob, which adjusts the digit, or you can just type it in. I usually find that to be easier, so we'll start with 1 and then megahertz. Still a sine wave, amplitude is 5 volts, but before we see a signal, we must turn on the output. So we'll turn on the output and we see a signal. Pretty small signals over here on the scope, so we'll press the auto button. It's okay to use the auto button anytime, but be a little careful in using it because it resets the scope each time you do so. So we have 2 signals shown. The yellow is our input signal, channel 1, and the blue is the output signal, which is channel 2. Now in this case we're going to be measuring amplitude and phase relationships. So one nice feature on these modern scopes is this is the vertical control for channel 1. If I press this button, you'll see that that is automatically centered in the middle of the screen. That's particularly useful for making phase type measurements. Now whenever you make a measurement on the scope, you should adjust the values such that the signals are at least 1/2 the screen size, and that is good for resolution. If I go any lower, it overranges. We don't want to do that. So we've set that out. Now you'll notice that the display is a little spiky in there, and that's associated with the data acquisition. So I'm going to press the acquire button, and change my acquisition to averaging. Okay, when I do averaging, you can see got a little smoother. Also, I can see that I can turn my knob here and adjust the averaging up. Generally, somewhere between 32 and 128 averages is good. It depends on your time base. The faster your time base will refresh sooner. So now we see the little bit nicer looking display in terms of the smoothness. But we also want, in this case, we're using ×10 probes on our scope. Generally, if you're going to work over a couple hundred kilohertz, you should use a scope probe. So if I press 1, I can set the scope ratio. Now, if that was set by the last user, it may or may not be in your configuration. So you should always check that. So I'll adjust down to ×10, press the button, and I see the ratio. Now that's important because that determines the values that are displayed on the screen. The scope itself doesn't automatically recognize the ×10 probe. We'll set the other channel to also be ×10. Alright, now we're ready to take some measurements. Now on the Regal scope, all of the measurements are set up on the left-hand side. Okay? So what we do, if we want to take a measurement, you can hit the menu and you can see there's a horizontal measurement screen and a vertical measurement screen. So let's set up the acquire or a measure button here. So we'll do measure and we'll see that this source is set to channel 2. So I'm going to change that to channel 1 because I want to measure the input voltage on the scope. So I'll go back to the vertical screen over here. I like to use the RMS measurement. So I'm going to select that. And you'll see that at the bottom of the screen, it now indicates the RMS value in yellow. You know it's channel 1, 1.72 volts. If I want to do channel 2 output, I select the source to be channel 2 and then press VRMS again. And now I have the output voltage, which is 1.21 volts. And those are RMS values. The next thing that we typically want to do is measure the phase between them. Phase is a time measurement, so that's the horizontal. So we press the button. Now phase is not on the first set of screens, but on the next one. You'll see phase 1 to 2. Now there's 2 of them here. It's a little hard to tell, but these are the rising edges and these are the falling edges of phase. Doesn't really matter, but we'll measure the rising edges. So now we see the phase measurement. Okay? Now you'll notice that that measurement jumps around a little bit. If the measurement values are a little jumpy, you can let it average for a little bit and then press the run stop button so it turns red and you can read off the values without having to interpolate in your mind the difference between them. The only trouble is that if the red button is on or the stop button is on, it will not be acquiring data. So if I make a change on the function generator, for example, you don't see a change until I undo the stop button. So be careful about using that stop button. It's nice in some cases, but has a problem in others. But useful for freezing values so you can read them off and record the data. Now, in terms of recording data, we can also use the USB stick method. So you see a USB port on the unit. So let's set that up. USB device. So I insert it, and you'll see a window pop up saying the device was detected. Now we're going to go and store the data. So when I go to storage, you'll notice on the top I can store traces, I can store waveforms, setups, pictures, or CSV, comma separated variable. The traces, waveforms, and setups are specific to the instrument, so the most common things that you will do will save as a picture. Now in the picture type, you can see that you can do BMPs, which is paint file, type files, PNGs, JPEGs, or TIFF files, which are image files. BMP is the largest type, JPEG is next, and PNG and TIFF files are generally smaller. So if you want a small file, use PNG. If you want to be able to edit it in Paint, use a BMP or whatever you're comfortable with. Let's go back to CSV. So CSV is commonly used with spreadsheets. Comma-separated variable files can be read by MS Excel. So all you have to do is, if you want to save a picture file, select that. Then we're going to go to Save, and it'll say where. Then you can pick your file type. There's the structure. There's my flash drive, disk D. You can see I have a couple folders here. I already created a Regal Scope folder. So inside there is a TIFF folder, a file, and I can save the file directly that way. So if I go Save, it's going to save the data. Alright, so now it's already created the file, it's saving it, and now I'm ready to go and look at the files. So we'll look at both the image files and the comma-separated variable file. So this is my Regal folder on my flash drive, and you can see I've got a file with the BMP, JPEG, TIFF, CSV, and PNG. The image files are very straightforward. You'll see this screen. That is actually the PNG file. This is the TIFF file. This is the BMP file. And that is the JPEG file. They all look the same in the Windows Photo Viewer. So now we'll look at the new file, the CSV file. If you double click on that, it'll automatically open up in Microsoft Excel. You see the X data, which is the time data. You see channel 1, channel 2, voltage data. This is the starting data, and here's the increment or the time step data. Normally what you will do, you will simply select the data. You will go to insert on a XY or scatter plot, and then we have our screen for our data. Now this data is plotted as in increments, so there's no specific time in there. If you want to use the values, you need to use the start time and then the increment to go through the actual time to do period measurements. There's looks like there's around 1,399 data points saved in the file, so that's really 1,400 data points. And then of course you can process this data using MS Excel. Make sure you save it as a Excel file. When you do that, if you go File, Save As, select and add that as a Excel worksheet file, a .xlxs, and save, and then you'll have an Excel file that you can manipulate within Excel. CSV files can only support one sheet, not multiple sheets, and a variety of other differences with a standard Excel file.